All right. Okay. So we're doing chapter 8 now. We've done confidence intervals. Well, I'm going to review the confidence interval that we calculated last time. I'm going to review it briefly today, and then today we will also cover effect size and statistical power. We will finish chapter 8 today. Before I get started, anyone have any questions or comments about things in general that we should talk about before we do this? All right. If people want to talk to me after class, I think we'll get done about 10 minutes early. We can talk then. So here is the confidence interval that we calculated yesterday. There's the lower bound and the upper bound of the confidence interval. It might help actually to show this picture right here. This is the confidence interval, like a pictorial view of our confidence interval. 89, which is our sample mean. To remind you, this is the mean score of people that received math drug, was 89. And these numbers right here are critical z-scores. This is negative 1.96, and this is positive 1.96. The reason we have these two z-scores marking right here is because they mark the boundary into the critical region, which is the shaded area right here. And then looking at this graph, you can clearly tell that this is a 95% confidence interval, which means alpha is 5%. We know alpha is 5% because if we add up the percent, 2.5% is in this tail, plus 2.5% in this tail. The total of a percent of the distribution, which is in the tails, the total percent of the distribution, which is critical regions, is 5%. We know this is a 95% confidence interval because if we look at the white region here, this is the center region. If you add up this percentage, 47.5 plus 47.5, this inner part, the part surrounding the 89, the part surrounding the sample mean, this is 95% of the distribution, while there is 5%, 2.5 in each tail, 5% total in the tails. So we have this is the confidence interval right here. Here's the general equation, and here's the specific confidence interval that we made earlier, we made last class. So to point out something, it contains, the M lower contains the critical z-score. This is a critical z on the left side of the distribution, and the upper bound contains the other critical z, positive 1.96. And so we're using this particular critical z because we're doing a 95% confidence interval. Once again, a 95% confidence interval means that 95% of the area is in the center part right here. 95% is this, 5% is in the tails. So our alpha is 5% because 5% is in the tail, which means that we're doing a 95% confidence interval because 95% is in the center part. I want us to think about what would happen to these numbers, these critical z numbers right here, negative 1.96, positive 1.96, if instead of doing a 95% confidence interval, we did a 99% confidence interval. And so thinking about what would happen if we did a 99% confidence interval, what that would mean is 1%, if we do a 99% confidence interval, 99% of the area would be in the center part. And then the two tails would only have 1% if you add them together. If we're doing a 99% confidence interval, this tail would have 0.5% of the distribution in it, and this other tail would have 0.5% because 1/2 plus 1/2 equals 1%. If there's 99% in the center, that means that there's 1% total in the two tails, 0.5% in each tail. And so if we're doing a 99% confidence interval, we need to think about how would these critical z's change. Remember, these are the critical z's that correspond when alpha equals 5% for a two-tailed test. Our critical z's are plus or minus 1.96. But if we're doing a 99% confidence interval, which means alpha is 1%, alpha is 0.01, we need to think about how do these critical z's change? And the answer is these critical z's would move further into the tails. The two critical z's would get further away from the center of the distribution. I don't remember the critical z for alpha equals 1% off the top of my head. It's like plus or minus 2.3, something along those lines. And so if we were doing a 99% confidence interval, instead of having the numbers negative 1.96 here and positive 1.96 here, we would have like negative 2.3 and positive 2.3, because if you're doing a 99% confidence interval, you have to move those critical Z's further into the tails. And what that does is that makes the total alpha level smaller. Instead of being 5% in the tails, like you see in this exact picture, if we're doing a 99% confidence interval, you push the critical Z's further away from the center of the distribution to make the percentages in each tail smaller. Okay, so now we're going to talk about effect size. And our effect size that we're going to talk about is this thing, Cohen's d. And the main thing that we're going to do today is we're going to compare Cohen's d to these other two things, which actually look quite similar. So we've calculated z-scores. We've been doing that now for a long time. In the past couple of weeks, we've started calculating z-scores for means. And I'll remind you, the primary difference between these two equations is, well, here, the x refers to a single value, a single raw score, a single data point. And when you're just doing a single score, so like you might want to know something like how much area is to the left of, you know, student X, some student's score, how much, what percentile is this student on the test or in the class? How many people, what percentage of the class is to the left of a given student's score on a test? A single, you're wanting to know the information about a single student, a single score. The sample size is 1, in other words. That's when you use this equation right here. We've been doing that for a while now for z-score for an individual score, which basically the sample size equals 1. The one that we've been doing more recently, which is more relevant to inferential statistics, is we'll be calculating z-mean. And a z-mean, we randomly sample from a population multiple scores. We add up those scores, and then we divide by the number of scores. That is, we take multiple scores from a population and create an average out of those scores, which, by the way, is what M denotes. M denotes a sample mean, whereas X denotes an individual score. Individual score, sample mean. And if you notice that in the denominator of the z-mean equation, there's this thing. Can someone remind me, what is the name of this thing right here?
Standard error.
Thank you. Yes, this is the standard error right here. It is defined as the population standard deviation divided by the square root of the sample size. And contrasting that with what's over here, which is the population standard deviation. When we're dealing with a single score, the denominator is just population standard deviation. But when we're taking multiple scores and then we're taking the average and then we're creating a z-score out of that average, which is what M stands for, the thing which is in the denominator is the standard error. So today we're going to be dealing with Cohen's d, which is a measure of effect size. And Cohen's d has things in common with each of these other two z-scores. So if you look at Cohen's d here, the numerator, m minus mu, the top part of the ratio, the top part of the fraction, is exactly the same, m minus mu, as this thing right here. So it has the numerator in common with the z-mean equation. But Cohen's d, if you look, the denominator is this population standard deviation, and it has that in common with the z-score equation. So this is what we're going to be dealing with today, Cohen's d, which takes part of each of these two. These are the two main types of z equations that we've been using so far for single score, for a sample mean. Cohen's d is kind of a combination of both of these things. So what Cohen's d is, it is a measure of effect size. And the best way to think of this is it measures the degree of separation between two distributions, and specifically what those two distributions are: a sample mean distribution, like the distribution of sample centered around the sample mean, and a distribution centered about the population mean. So basically, how far apart is the sample mean from the population mean? So that's what Cohen's d is. And Cohen's d is it's influenced by several things, and it has some interesting properties. So first, the bigger the mean difference between the sample mean and the population mean, the bigger the effect size. And looking at this equation, you can see that, right? If you look at the numerator right here, you have m, the sample mean, minus mu, the population mean. The further apart these two numbers are, the further away the sample mean is from the population mean, the bigger a number you're going to get here in the numerator. The bigger the difference between these two means, the bigger the numerator is going to be, the bigger the top part of this ratio, the bigger the top part of the fraction. And as the numerator gets bigger, the overall Cohen's d value gets bigger as well. As the numerator gets bigger, Cohen's d gets bigger. additionally, the smaller the population standard deviation, the bigger the effect size. So this is something we need to think about a little bit carefully. It might be a little bit, it takes a little bit more cognitive power to understand what's going on here. The smaller the population standard deviation, the bigger the effect size. So we need to think about why that is. And the reason is because population standard deviation is in the denominator. And the denominator is the thing that you're dividing by. And if you're dividing by a big number, that makes the overall ratio small. If you're dividing by a small number, that makes the overall ratio relatively bigger. So when this number right here, the standard deviation, when the standard deviation is small, that makes the overall measure of Cohen's d, that makes the effect size bigger. So to kind of repeat here, when the numerator gets bigger, Cohen's d gets bigger. When the denominator gets smaller, Cohen's d gets bigger. When the numerator gets bigger, Cohen's d gets bigger. When the denominator gets smaller, Cohen's d gets bigger. And probably the most important conceptual thing about effect size, the reason they're even worth calculating at all, is because measures of effect size are not influenced by sample size. And we're contrasting that with Z-mean in particular. And I'll show you an example here that illustrates this pretty concretely. If you look at the equation for Z-mean right here, this is one we've been dealing with for the past couple of weeks, you see that it has the square root of the sample size right here. And we need to be interested in, or we're interested in, how does the value of Z change depending on the value of the sample size? And the general rule of thumb is, if the sample size is small, then that's going to cause the standard error to be big. If the standard error is big, that causes the overall ratio to be small. So that's several steps there, so I'll repeat it. If the sample size is small, that causes the overall standard error to be big. If the overall standard error is big, that causes the overall ratio, the Z-mean, to be small. However, if the sample size, as the sample size gets bigger, as n gets bigger, the size of the standard error gets smaller. As sample size gets bigger, the size of the standard error gets smaller. Because the standard error is the denominator, as it gets smaller, the overall magnitude of Z-mean gets bigger. So as sample size gets bigger, standard error gets smaller, which causes the overall magnitude of Z-mean to get bigger. But notice how Cohen's d is different. Cohen's d does not have the square root of n in the denominator. So as sample size increases, as the sample size of m increases, it does not affect the denominator at all. For the Z equation, as the sample size of m increases, it causes the overall standard error to get smaller, which increases the magnitude of Z-mean. For Cohen's d, there is no square root of n in the denominator, so the sample size has no influence of the magnitude of Cohen's d. I'll show you that with a mathematical example here in a second. But that reinforces this idea. Measures of effect size like Cohen's d are not influenced by sample size, whereas the Z-score for Z-mean most certainly is influenced by sample size. So a little bit more just conceptually about what effect size is. There was those two bullet points. The bigger the mean difference, the bigger the effect size. And that's what we're talking about here. The bigger the mean difference, the bigger the effect size. So these are two distributions. One of these, here's example A, here's example B. For each example, one of the distributions represents the sample mean. So we'll say that this represents the sample mean. The other one represents the population mean. So one distribution is the sample mean, the other was the population mean. These vertical lines here are the center of the distributions. That is, they're the mean of the distributions. And so you notice how in example A, the means of these two distributions are relatively close to each other. For sample B, the means of the two distributions are relatively further apart. And so we want to think, in which of these two examples, example A or example B, would we have a bigger effect size? And the answer is example B. We would have a bigger effect size because the distance between m and mu is big here. M minus mu is a big difference here, which would give us a big numerator for our calculation of Cohen's d. For this example right here, the distance between m minus mu is a small one, So we would get a relatively smaller number in our numerator. So the further apart the means of our two distributions are, the bigger the numerator is going to be, or at least the further the numerator will be from 0, which will give us a bigger effect size. The further away the two means are from each other, the bigger our measure of effect size will be. So this is illustrating the first point right here. Bigger the mean difference, the bigger the effect size. The second point that I want to illustrate with the drawing is the smaller the population standard deviation, the bigger Cohen's d gets. The smaller the standard deviation, the bigger Cohen's d gets. And that's illustrated by these two examples right here. So a couple of things about these two examples. For both examples, you'll notice how the vertical bars line up. So remember, these vertical bars represent the mean of each distribution. So this is the sample mean right here. This is the mean of the sample distribution, and this is the mean of the population distribution. So you can see that they have a m minus mu. The distance between these is some number right here. But right here, the distance between the sample mean and the population mean is the exact same distance. You can see that because these lines line up perfectly. The vertical lines with example A line up perfectly with the vertical lines from example B. The distance between the two means is the same here as it is right here. So in other words, the numerator, m minus mu, for the Cohen's d we would calculate here, and the numerator for the Cohen's d that we would calculate here is the exact same. The distance between m minus mu is the same. But you can see, hopefully, that the standard deviations of the distributions up here are bigger than the standard deviations of the distributions down here. And you could tell, this is something that I mentioned, it's been a while, but I definitely mentioned this earlier on in the semester, that you can look at a histogram, you can look at a distribution, and you can tell whether the variability of the distribution is big or small by looking at how wide or thin the distribution is. If you look at these distributions, you can see that they're wide. What that means, what that represents, is the fact that the variability, the standard deviation of these distributions is big. Here, down here, the standard deviation of these distributions is small. We can tell that because they're thin. They're narrow-looking distributions. And if you actually look here, the effect size would be, even though the distance between the two means, m minus mu is the one distance here, m minus mu is the exact same distance here. So the numerator for Cohen's d here is the same as the numerator for Cohen's d here. Because the standard deviations of our distributions are different, we would actually get a bigger Cohen's d down here. Because, as is mentioned on the previous slide, when the standard deviation is small, you have a small number in the denominator, that causes the overall ratio to get bigger. When the standard deviation is small, Cohen's d tends to be big. And if you actually look at this, we're thinking about what effect size is conceptually. Effect size is the measure of separation. It is how far apart two distributions are. And if you actually look at these distributions look further apart. They have less overlap between them. This is the degree of overlap here. There's a lot more overlap here. And the reason there's more overlap here than there is here is because, once again, the variability is small here, which means there's less overlap, which means there's relatively more separation here, which results in a bigger Cohen's d. There's relatively less separation here, which results in a smaller Cohen's d. Any questions or comments so far? Okay, so the last bullet point here, measures of effect size are not influenced by sample size. So we've already kind of talked about that, why that is, because the Z-mean equation has the sample size in the denominator, where the Cohen's d equation does not have the sample size in the denominator. So I want to give a concrete example. The book doesn't really provide an example of this. And so I'm providing a very concrete example to illustrate this third bullet point about how Cohen's d, the measure of effect size, is not influenced by sample size, but the Z-mean is influenced by effect size, by sample. Z-mean is influenced by sample size, rather. Okay, so let's look at this example. So for each example, here's example A, here's example B. We have the exact same population. So here's a very small population. There's only 8 people in the population. Everyone in the population happened to get a score of 4 or 6. Let's just pretend that it's some score on a quiz or some measure of intelligence or something like that. These are the scores of all the people in the population, very small population. It's the exact same population over here. So the same population you see right here is the exact same population you see right here. The difference between these two examples is the size of a sample. The difference between these two examples, A and B, is the size of a sample that we are calculating a mean for. In example A, as it says right here, our sample size is 2. So what that means is we have this population with 8 people. We're going to randomly choose 2 scores in this from this population, add up those 2 scores, divide by 2. That gives us a sample mean. And we'll say that M stands for sample mean with the sample size of n equals 2. Let's just say that we did that and we got our sample mean gives us a value of 6. We take 2 scores, add them together, divide by 2, and we get a sample mean of 6. And we do the same thing for example B, but instead of using a sample size of 2, we're going to do a sample size of 4. Let's say once again that when we add up those 4 numbers, randomly pick 4 numbers from up here, we add them together, divide by 4, the mean of that sample size once again is 6. So in this example, the mean M, sample mean, equals 6, but it's based on a sample size of 2. In this example, the sample mean M is still 6, but it's based on a sample size of 4. And so the question is how does Cohen's d and Z mean, how is it influenced by the fact that here our sample size of 4 is relatively bigger than example A when the sample size was 2? And so I've shown all the answers. I guess I should show you my work here as well. So if you look in the notes portion of the slides, I've calculated Cohen's d for example A, Cohen's d for example B, Z mean for example A, and Z mean for example B. So I've shown you all of the work for how I got all of the numbers that are in here. But I kind of want to walk through it. So this is when you're studying later, if you're trying to reinterpret this and you forget what I've said right here, right now, you can see my work in the notes portion. So don't forget about that. But let's kind of go through things here. The population standard deviation. So if you take the standard deviation of these 8 numbers right here, the standard deviation happens to come out very nicely, 1. This is the standard deviation of the population. And it says that we got a Cohen's d of 1. So I want us to work through Cohen's d and figure out why that is. Thinking about the formula for Cohen's d, it's the sample mean minus the population mean divided by the population standard deviation. And so the numerator of our Cohen's d is m minus mu. What do we get? Looking at these numbers, what do we get when, I want someone to help me out here. What do we get when we take m minus mu? What does that equal? M minus mu.
1.
Yes, thank you. It is 1 because 6 minus 5 equals 1. So the numerator of our Cohen's d in this case is 1. And remember, Cohen's d is dividing by the population standard deviation, which is also 1. So 6 minus 5 equals 1. 1 divided by the population standard deviation of 1 equals 1 divided by 1 equals 1. That is why our Cohen's d right here is 1. Let's do Cohen's d over here for the sample size of 4. You notice that it doesn't change. It's the same thing. 6 minus 5, that's our numerator when we're calculating Cohen's d over here. 6 minus 5 equals 1. The population standard deviation doesn't change because it's the exact same population, right? Exact same population. So the population standard deviation is still going to be exactly 1. 6 minus 5 equals 1. 1 divided by 1 gives us a Cohen's d of 1. So what this is showing so far is that take a sample size of 2, our Cohen's d is 1. Take a sample size of 4, our Cohen's d hasn't changed. It's still 1. This is reinforcing the point I made a couple slides ago that Cohen's d is not influenced by sample size. And we're going to contrast that with Z mean. Z mean definitely is influenced by sample size, and that's what I'll show you now. So remember, the numerator of Z mean is the exact same as the numerator of Cohen's d. So the numerator of Z mean is still 6 minus 5, which is 1. So when we're calculating Z mean, 6 minus 5, that's the numerator. That's the top part of the ratio for Z mean. But if you recall, for Z mean, the denominator is the standard error. And we should probably remember what the standard error is. The standard error is the population standard deviation divided by the square root of the sample size. So our standard error is the population standard deviation, 1, divided by the square root of our sample size, which is 2. 1 divided by the square root of 2, that gives us our standard error, which is this long decimal right here, 0.707, etc. This is our standard error, which is 1 divided by the square root of 2 gives us this thing right here. So this is the denominator of our z-mean, remembering that the numerator, 6 minus 5, was 1. The denominator is this number right here. 1 divided by this number right here gives us a z-mean of 1.414, which is this value right here. So now that was the z-mean for a sample size n equals 2. Now we need to do a z-mean for a sample size n equals 4, and we will see that it does change the value of z when the sample size increases. Once again, the numerator is m minus mu. 6 minus 5 is simply 1. That is the numerator. But we need to divide the numerator by the standard error. And you notice our standard error is different. Why is our standard error different? Over here it was 0.707. Now when we calculate standard error, it's 0.5. Why is our standard error different? It's gotten smaller in particular. Why has it gotten smaller?
Because the sample size increased.
Yes, thank you. We're now dividing by the square root of 4, which, by the way, the square root of 4 is a nice number 2. So the numerator, 6 minus 5, is 1. But we're dividing by the standard error, which is 0.5. The reason why the standard error is 0.5 is because our standard deviation is 1, but we're dividing that by the square root of 4, which is 2. 1 divided by 2 equals 1/2, or 0.5. So 0.5 is the number which is in the denominator. So we're taking the numerator, which is 1, 6 minus 5 equals 1, dividing that by 0.5. 1 divided by 0.5 gives us a z-mean of 2. So now we've really illustrated what I was saying on that a couple slides ago, that whereas Cohen's d is not influenced by sample size, Cohen's d is 1, whether our sample size is 2 or whether our sample size is 4, we get the same Cohen's d, exactly the same Cohen's d. But if you look at the z-mean, the sample size, as it increases, it causes the standard error to get smaller. 0.5 is smaller than 0.7. As sample size increases, it causes the standard error to get smaller. And because the standard error is in the denominator, it causes, when the standard error gets smaller, it causes the magnitude of the z to get bigger. 2 is bigger than 1.414. So this illustrates, once again, this idea. Measures of effect size are not influenced by sample size, but z-mean is influenced by sample size. The reason z-mean is influenced by sample size is because it contains the square root of n right here as part of the standard error. As this thing gets bigger, the standard error gets smaller, which causes the overall z ratio to get bigger. Questions or comments about that? Okay, one more thing about effect size, and we'll go to power. Okay, so this is, these conventions for what does a different effect size mean. I'm showing you this because I know that there's a question on test 3 about this. I find these values, these Cohen's conventions for effect size to be a little bit arbitrary and not that important in the big scheme of things. But there is a question about this on the test, so I'm going to talk about it. So this right here, this is a Cohen's d of 0.2, 0.5, 0.8. And the convention is if you have a Cohen's d of 0.2, that's considered a small effect size. 0.5 is considered medium. 0.8 is considered large. In the notes portion, I note that in general, if you have an effect size that is 0.2, that is smaller than 0.2, then your effect size is so small that it's considered basically negligible. So smaller than 0.2 basically means there is no effect size. It's basically 0. It's negligible. And so these are just conventions, like, if you have these effect size, if you calculate Cohen's d and it's 0.8, that's generally considered a big effect size. But I also want to point out that what these numbers represent is the amount of standard deviation units that separate the sample mean from the population mean. So if my Cohen's d is 0.8, what that means is that the sample mean and the population mean are 0.8 standard deviations apart from each other. If I get a Cohen's d of 0.2, then that means that the sample mean and the population mean are 0.2 of a standard deviation away from each other. And this has to do with the fact that Cohen's d, it measures the degree of separation between the sample mean and the population mean in terms of population standard deviation units. It measures the degree of separation between these two means in standard deviation units. Cohen's d of 0.8 means that there's 0.8 standard deviations. 8/10 standard deviation separate the two means. Okay, so that's it for effect size. Now we're going to talk about statistical power. And here with statistical power, I'm definitely choosing to lecture about the things that I noticed are covered most heavily on the test. So I'm really teaching almost right to the test. I'm teaching for the test, basically, about statistical power. Just about everything we're talking about, I'm talking about it because there's a question related to this on the test. So first thing, here's the definition of statistical power. The probability of rejecting the null hypothesis, given that the null hypothesis is false. There is a question on test 3, which is basically that requires you to know this definition right here. So I'm giving you this definition because I know on test 3 that there's a question that requires you to know this definition about statistical power on the test. So I'm showing you this, but I kind of prefer thinking about statistical power using these things right here because I've restated this definition of statistical power using language, which is, in my opinion, a little bit easier, a little bit more down-to-earth language. So although this is true, it might be easier to think of statistical power as the probability that we will find a significant effect when the effect is, and I put in quotes, real. And what I mean by real, that means in real life, this is a real legitimate phenomenon that occurs. And that's what is meant by real, that the phenomenon that we're studying is real. We should find a statistically significant difference between what the two means that we're comparing. However, it turns out because of probability, because of chance, there might be a phenomenon that you're studying where in reality the means should be different. Like the phenomenon is real, therefore that we should find a treatment effect. We should find that the means are separated. But sometimes, just because of chance probability, you'll collect data and your hypothesis test will say, no, there is not a statistically significant effect. It doesn't happen a lot, but statistically it's going to happen sometimes. There'll be an effect that's real, but it'll be called a false negative. Sometimes you'll get a false negative where you should get an effect, but just because of statistical chance, because of probability, you'll get numbers that will result in you not rejecting the null hypothesis. You'll get numbers that you end up not finding a statistically significant difference, even though in reality you should have found a statistically significant difference. So statistical power, the probability that we find a significant effect when we should find a significant effect. Sometimes you won't. Small percent of the time, you're not going to find a statistically significant effect, even though you should. The probability that we do find one is statistical power. The probability we find a significant effect when the effect is real. Another way of saying this is the probability that we avoid a false negative. The probability that we do not commit a false negative. The way the textbook words this one, by the way, is they say the probability that we will avoid a type 2 error. But I'm just reminding you, a type 2 error basically means false negative. I've always hated the language type 2 error because you have to really think, what is a type 2 error again? A type 2 error is just a false negative. So there's two different ways of thinking about statistical power. This is the formal definition. These are kind of gives you in more simple language what statistical power is. So the factors that affect statistical power, the book talks about 5 of these. I'm only going to talk about 2. Because they're the most important, arguably, of factors that affect statistical power. The magnitude of alpha is number 1. So remember, in psychology, the typical alpha is 5%, or alpha equals 0.05. Alpha equals 5%, or 0.05. What that means is alpha equals 5% means 5% of the area is in those tails. If you increase alpha to say 10%, we make alpha instead of 5%, we increase alpha to make it 10%. What that means is there's now going to be 10% of the area is going to be in those tails. In order for there to be 10% of the areas in those tails, what we have to do is we have to move those critical z's closer to the center of the distribution. That causes, instead of there being only 5% total in the distribution, if we move the critical boundaries closer to the center, then we're going to have more area. Instead of 5%, we'll now have 10% of the area in our critical region. And if the critical region gets bigger, that is, if we move those critical boundaries closer to the center of the distribution, what that means is we have a higher likelihood that when we calculate our Z mean, when we calculate the Z-score for our mean, and then we plot it to see if it falls in the critical region or not, if we have increased the size of the critical region to 10%, it now covers 10% of the total distribution. If we've increased the size of the critical region by increasing alpha, then what we've done is we've increased the likelihood that our Z mean is going to fall somewhere in that critical region. And remember what the critical region means. The critical region is that part of the distribution where if the Z mean falls into the critical region, we reject the null hypothesis. We conclude, yes, there is a statistically significant difference. So if we increase alpha from 5 to 10%, let's say, then what we're doing is we're increasing the size of the critical region. As we increase the size of the critical region, that increases the likelihood that we reject the null hypothesis. That increases the likelihood that we find a statistically significant effect. That increases, therefore, the statistical power that we will have, increases the likelihood that we will find a significant effect. So that's the magnitude of alpha. For sample size, as sample size increases, well, what that does is that decreases the standard error. We've already talked about this. When we're calculating Z mean, the sample size, the square root of n, is in the denominator. We've already said as sample size increases, that decreases the standard error. Because the standard error is the denominator, as the standard error gets smaller, the overall Z mean gets bigger. The overall Z mean is getting further from zero. The further from zero that the Z mean is, the more likely that Z mean is going to end up in one of the tails. The more likely that the Z mean is going to end up in those critical regions, in one of the critical regions. So increasing sample size also increases the likelihood that we'll find a statistical effect. Increasing sample size also increases our statistical power, because increasing the sample size decreases the standard error. When we decrease the standard error, it increases the magnitude of Z mean. And as we increase the magnitude of Z mean, the more likely Z mean is to fall into the critical region, which means we're more likely to find a statistically significant effect. Okay, so that's it actually for lecture stuff. Does anyone have any questions or comments? All right, I'll stop recording here.